All right, hi everyone. Thanks for the introduction. Before we jump into Piranha, I wanted to take a quick second to introduce multi-party computation, MPC, again. The idea of MPC is that you have several distrusting parties, so P1, P2, et cetera. They each have some sort of secret input that you want to compute a shared result. And the catch is that during this process, they don't want any of their private inputs to be leaked to any of the other parties. And so this is precisely the security guarantee that MPC provides. And so it's a really useful tool. But over the 40 or so years that we've been studying it, it's actually very, very expensive. So for example, generating a shared AES encryption in MPC might take up to a millisecond per block in MPC versus a couple hundred cycles on modern AES hardware. And in machine learning tasks such as inference, it's 4 orders of magnitude slower to compute securely compared to plain text. And that's not even to mention training ML models in MPC, which might take up to weeks to complete on a CPU. So speaking of ML training, I'm going to kind of quickly spoil Piranha a little bit and kind of tab to a live demo. So we're going to be training this model during the rest of the talk. I'm just going to run a very simple secure ML architecture. And if I don't mess anything up, we can, of course, the live demo doesn't work at exactly the same point. Vim, 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 vim. Nice, nice, nice. Whatever. We'll run it later if anyone wants to see it. But trust me, it trains. OK, so back to the slides. It's obvious that there's a massive, massive performance challenge here. And looking around, how do we actually fix this problem for plain text? Well, the solution to a wide variety of computational problems in that setting was using general purpose GPUs. So the point of this talk is asking, can we similarly apply them to generally accelerating MPC? So there's been some investigation in the space, but the reality of privacy-preserving machine learning training, for example, is you get to re-implement a lot from scratch when you want to try to start up a project. So on the MPC side, you're picking a protocol, you're implementing it, you're testing it, et cetera. And at the same time, if you want to use a GPU, you're wrangling the GPU to be able to accelerate each piece. So you're contending with data management. There's a memory hierarchy in there. You're building all the kernels for what you want to accelerate. And as a result, practically, there's a huge gap in capability between cryptographers who develop MPC protocols and systems experts who spend all day hacking on GPUs. So in this talk, I want to show you how Piranha bridges this gap between cryptography and systems and how it manages GPU concerns so that MPC experts can focus on designing protocols and the like. So at the high level, Piranha's big goal is to make accelerating secure MPC practical. And for this talk, we're going to focus on a subgroup of protocols called linear secret sharing protocols. And we're going to build support for them with 2 sub-goals in mind. So the first goal is that it should be usable. And that means that Piranha should be capable of supporting many different protocols and extending easily to new applications. And number 2, it goes without saying that it should be performant, right? It should actually be pretty fast. And so both goals seem pretty simple at the outset, and that's what we thought. But that's unfortunately not quite the case. And so to understand why, I want to take a quick tour of Piranha's architecture and point out a few big issues. So the first issue is this issue of unnecessarily duplicated work. So if you want to do privacy-preserving ML or any MPC computation, what you'll get is this monolithic application bundle that combines some custom protocol that someone developed and the application. But say you just went to a talk, you learned about some cool new inference protocol or Poisson regression, whatever you want, and that makes specific operations much faster. How do you actually integrate that into your project to gain the benefits? Well, you're kind of out of luck because existing components are just shackled together in a big blob that makes it impossible to use in a modular way. So Piranha takes that modular approach, and it uses a 3-layer design to split apart the neural network library at the top from the protocol in the middle, from the local GPU operations that we can focus on accelerating at the bottom. And importantly, this allows us to preserve the security properties of the MPC protocols, while at the same time clarifying this sort of separation of concerns, where Piranha accelerates computation, MPC developers can focus on composing that computation with communication, and applications can sit above it all and choose whichever protocol they want that fits the task. And this all works because LSS protocols, in essence, use the same local building blocks and differ mainly in how they apply local operations on their secret shares and how they communicate with other parties. And on the application side, applications just see data managed by multi-party computation protocols as just some sort of opaque data type that they can switch out with a single define. So this makes Piranha applications entirely agnostic to future changes in state-of-the-art multi-party computation. So to dig a little deeper, let's step into the shoes of someone with an application that's training a simple, fully connected neural network layer with a ReLU activation. This is exactly what I tried to run in the internet crapped out. So underlying that, protocols need to implement a secret shared matrix multiplication for the fully connected layer and a comparison for ReLU. And at the bottom, Piranha needs to provide kernels to accelerate those corresponding operations. And right here at the bottom layer is where we start running into both computational and memory problems. So problem number one is we somehow need to find a GPU kernel that can actually perform matrix multiplication for our protocols. Unfortunately, the really popular and highly optimized kernels for doing this, like cuBLAS, like the first thing you would Google, don't work for us because they only operate on floating point values. So our LSS schemes need to operate over integer rings. And in fact, there are no matrix multiplication kernels, for example, with the integer support that we need. So one solution is to embed, say, 16-bit chunks of the 64-bit integers we care about into 4 floating point matrices. And then you can use existing kernels to calculate a bunch of different pairings and then summarize them back into your final result. And unfortunately, that causes a lot of overhead. In this case, a 10x overhead in the number of matrix multiplications that you need to do. And importantly, this kind of system is based on an assumption, and that assumption is that because floating point kernels should be really, really fast, the end-to-end performance should outweigh the overhead. Now, in Piranha, we take a different approach. What if we just directly computed the integer matrix multiplication on the GPU using the GPU integer cores? And sure, individual kernel implementations might not be as crazily optimized as cuBLAS, but our view is that we should not get gains out of cutting out redundant computation. Or we should get gains, sorry. Yeah, we want the gains. So anyway, we leveraged NVIDIA's cutlist library to implement both 32-bit and 64-bit gem kernels. And when you compare them head-to-head, an individual matrix multiplication directly computed using integers is slightly slower than in floating point. But overall, we make a huge amount of time back by not repeating the same operation over and over. Okay, so that's one part. Okay, great. We have our integer kernels. Everything is hunky-dory. We're off to the races. And that's true until we run into trouble actually implementing some of the more complex parts of the MPC protocols, such as comparisons. So it's during this step that the constraints of GPU memory in particular becomes the overriding concern for executing multi-party computation. And the main issue is that, first off, replicated secret sharing inherently induces data duplication that stresses the memory limit, so like 16 gigabytes that we have on our GPUs. And a 3-party protocol, for example, might automatically double the memory load of a given computation compared to plaintext. And the problem gets even worse. So comparisons in particular are very good at exhausting GPU memory because they require a bitwise expansion, secret shared expansion of each value. So we go from 2 times to 10 times more memory pressure just from this expansion. So anything else we do is going to limit the problem size that we can support, and that's, you can think of it as like the model size for machine learning. So to illustrate this, let's look at a simple operation, which is to perform the multiplication of each bit in a bitwise string. It's slightly simplified, but it turns out that this is very useful for implementing secure comparison. So the basic idea is that in parallel, you want to multiply the neighboring blue and yellow bits together, repeating a logarithmic number of steps until you've coalesced the result into 1 bit. So it looks a little bit like this. So notice that in this implementation, to make each step in the process nice and vectorizable, we want to marshal every blue and yellow bit into separate vectors so we can multiply them all at once on the GPU. So unfortunately, doing this incurs constant data movement and reallocation. It makes it actually way slower than using a CPU. So how do we fix this? Well, Piranha allows protocols to use iterators to define in-place views over the same piece of data. It separates the protocol's data layout from Piranha's acceleration layer. And we can use that to replace marshalling data with an iterator to every yellow or blue secret shared bit, storing the result back in on itself. And we can repeat the process to effectively remove any data movement whatsoever, maximizing the remaining GPU memory to store larger and larger problems. Okay, so we saw Piranha addresses 2 big challenges in accelerating MPC, memory and computation. But at the end of the day, how well does it really work? So we implement Piranha in C++ and CUDA. Use it to develop a neural network training library that can execute on top of any of 3 MPC protocols, a 2-party secure ML, 3-party Falcon protocol, and a 4-party Fantastic Four protocol. And as a quick aside, you could add any protocol or other application on top of that you wanted to Piranha. And we encourage that, but for this, we focused on these 3. So looking directly at individual operations like matrix multiplication, we compare Piranha's performance to exactly the same protocol implemented in MP speeds on the CPU. And we demonstrate 273 times improvement at relatively large dimensions for a 3-party protocol. And it's not just this one protocol. Among all our protocols, Piranha shows orders of magnitude improvement in performance. And it's not particularly surprising that GPU makes the computation faster, but what is really important to point out is that generality in this case did not come with a performance penalty. Similarly, I want to demonstrate the massive difference that Piranha makes by using memory-efficient techniques. So this is the memory footprint of a single VGG forward pass, which naively requires almost 2.3 gigabytes, where the model size, the baseline, you can see at the bottom, is actually just 345 megabytes. If we implement the iterator-based change I discussed earlier, we can almost halve that memory use to 1.4 gigabytes. And we can reduce this significantly further by being careful about what types we use to store the expanded bits. So this allows us to tackle problem sizes that would be unachievable in prior work. And finally, is Piranha actually usable for something? So we took the same network, VGG, that was estimated to take 2 weeks to train on a CPU with over 100 million parameters. And we did a 10-epoch training run on a GPU. So Piranha completes this training in just 33 hours, a 10x decrease in training overhead. So to our knowledge, this is the first work to successfully train end-to-end such a neural network within secure computation. And you'll have to see me after for the demo if you want to see how that works. Okay. So to sum up, Piranha is a general-purpose platform for accelerating MPC on GPUs. There's a lot more you can check out in the full paper, but most importantly, you can find our code open-sourced at the link on the slide. So please come talk to me if you want to use Piranha to build and test new protocols or to implement new and exciting applications. And with that, I'm happy to take any questions. Thanks.